Now we can move on to the next simulation, which is of smoke rising from the ground. I divided the simulation into two sections. The first is a simulation within the actual scene. Then I made a new file that only contains the smoke that completely fills the viewport. In post-production, I used this animation to cover the entire scene. This can also be used as a transition to the scene where the pilot stands up. I won't go into too much detail about smoke and fluid simulations, because I've already published 2 classes on the platform. They are comprehensive courses on smoke, fire, and liquids. So, by watching those lectures, you can learn more about these topics. The basic setup for a smoke simulation is straightforward. Essentially, you'll need an object that serves as the emitter, and another as domain, which refers to the region of space where the simulation is taking place. Starting from scratch is the best way to demonstrate this. So, let's set up a new scene. After that, include the source of the smoke. It could be anything. In this case, a simple sphere. The quickest way to add the simulation now is to choose Quick Smoke from the Quick Effects menu. And we have the option of producing only smoke or both smoke and fire. In this case, all we need is smoke. Blender automatically adds this cube, which is the domain. It is the area where the simulation is run. The domain is important because it limits the amount of space in which the simulation can expand. Otherwise, it could grow indefinitely, consuming massive amounts of memory and computation power. The simulation's resolution is indicated by the small cube on the left. This will be demonstrated later. So Blender added the fluid simulation to this object automatically. Then, each object is automatically set as the source or domain. The ball is the source of the smoke, which is denoted by flow. The box, on the other hand, has the type property set to domain. When we begin the simulation, smoke rises from the sphere. It is discarded when it reaches the top of the domain, so it is not computed outside it. Now, let's select the source. We can specify the type of simulation we want in the flow type property. As you can see, you can also select liquid. Indeed, liquid simulations share many properties with smoke simulations. They all fall into the category of fluid simulations. This is also good news for us, because the concepts we learn can be applied to both types of simulation. We can now control how the smoke behaves. The term inflow refers to the continuous and never-ending emission of smoke. The term outflow refers to a smoke-absorbing object. You could look at this as a form of suction fun. In contrast, geometry generates smoke that can be contained within the volume of the source object. As a result, the smoke is not continuously emitted, but its volume is the same as the emitter. Nothing happens if I change the setting to geometry and run the simulation. The simulation is identical to before. This is because we have to reset the simulation every time we change or update a parameter. Otherwise, we're back to the previous simulation. The best way to reset the simulation is to select the domain and change the resolution divisions options. By doing so, we effectively force Blender to restart the simulation. Then, as with all simulations, we can rewind the timeline and start from the beginning. Now we can clearly see that we have a limited amount of smoke. We also have other options, which we will discuss later. Set the smoke to inflow once more. And, once again, I must restart the simulation from the beginning. Let's look at some of the domain's properties now. The resolution divisions is one of the most important option. It represents the simulation's resolution and is calculated in voxels. Consider voxels to be 3D pixels. And this is clearly visible here. The actual resolution is represented by the box on the bottom left. And it is clearly related to the resolution of the smoke. And by increasing the resolution to 64, we can see finer details. As a result, we'll need to significantly increase the resolution for the final rendering. As you can imagine, this will increase the computation time. You can leave it between 32 and 64 for testing purposes. The timescale is another interesting parameter to consider. It essentially accelerates or decelerates the simulation. It is also useful for slow motion animations. We'll discuss the other options later in this course. The border collision option specifies how to handle the fluid when it reaches the domain's boundaries. It is simply discarded by default. However, we can also allow the domain to act as a real container, causing the smoke to hit and bounce off the walls. And you can do so by selecting the desired wall, in this case, the top one. By the way, when I select one of these options, the simulation is reset, just like when I changed the resolution. The smoke is now interacting with the top wall. Then there are other options, based on the fluid's physical properties. The buoyancy density represents the tendency of smoke to rise, or stay close to the source. We also have the properties, heat, and vorticity. The dissolve option, as the name implies, simulates how smoke fades over time. We also have the noise property. It changes the shape of the smoke. However, as we will see later, it also increases the resolution. We also have the cache option here, and we'll see how to manage it. Well, as a final example, I'll show how to create the same simulation from scratch, without using the quick smoke effect option. Let's add a new emitter, in this case a torus. I'll also include a cube that will serve as the domain. Add the fluid property to the emitter. Now, select the domain, add the same property, and set the type to domain. Now, select again the emitter. Select flow as the emitter type and smoke as the flow type. Finally, choose inflow as the flow behavior. And this is what happens. As can be seen, the smoke has a similar shape to the emitter. This is important, because we can greatly improve the realism and power of a simulation by carefully selecting the right emitter. Now we must incorporate the smoke simulation into our scene. It must be emitted where the spaceship collides with the ground and move with it. After such an impact, it must also behave like real smoke. As a result, it must first expand horizontally before gradually moving upwards. As a first step, we must design the emitter, which will be placed where the spaceship's central body collides with the ground. So we could make a simple object with a flat shape that moves with the spaceship. Let's start by adding a simple box and scaling it along the z-axis. As previously stated, modeling a proper emitter is critical for a realistic simulation. For example, in our case, we do not want the smoke to be emitted uniformly from the emitter. We expect an uneven distribution of smoke when the spaceships hit the ground, based on the parts of the spaceships that hit the ground. As a result, editing the emitter to split it into multiple separate objects may be useful. So, in edit mode, duplicate the object, and move and scale the copies in various locations. In this manner, we will generate smoke from various sources. We also want the emitter to follow the spaceship. We can accomplish this by manually animating the object's location and rotation. We must now add the domain. As previously stated, it is a simple cube. It is important to note that we must scale the domain so that it does not become too large. It must only be large enough to hold the volume required for the simulation. As a result, we are able to optimize the computation. Furthermore, if we have a domain that is larger than what we require, we will reduce the final resolution. Consider this domain, which is larger than what we require. When we increase the volume, we also increase the size of the voxels. It's the same idea as increasing the size of an image. As a result, the image is larger but has lower resolution. Well, let's change the cube's display mode to wireframe. Now, let's scale and position the domain to exactly where we want the simulation to take place. Following that, the scale must be applied. This means that Blender treats the new size as the original size of the object, which avoids some computation issues. When we open the property panel, we can see that the scale property has different values. We basically need to reset these values to 1, as if this new size was the original. Simply select the object, and press the Ctrl and A keys to do so. Select Scale. In the Properties panel, the scale is reset to 1. Now, add the domain smoke property to the cube. Repeat for the emitter, but this time select Flow. As we want the smoke to be continuously emitted, the flow behavior must be inflow. The next step is to start the smoke simulation only when the spaceship touches down. We can do this by selecting the domain, going to the cache section, and specifying the start and end frames for the simulation. By the way, we can see that Blender automatically creates a cache folder. However, we'll discuss how to properly cache the simulation later. We can now begin the simulation. The smoke is produced when the spaceship collides with the ground and moves with it. Obviously, this is a low-resolution version of the simulation. We require this in order to see a quick preview. This can also be used to resize the domain. Indeed, we notice that it is excessively large in comparison to the simulation. As a result, we can scale the domain to be slightly larger than the smoke. To reset the simulation, change the resolution division. And we can restart the simulation. Now we must fine-tune the simulation to achieve the desired result. We must now modify some simulation settings. First and foremost, we notice that the smoke remains in the same position. It should at the very least move in the same direction as the spaceship. We must also control how the smoke dissolves over time. So, consider some of the emitter properties that we didn't consider previously. The initial temperature influences how the smoke rises. The term density refers to the density of the smoke. And this is the first thing I'd like to change. The smoke is immediately generated when the spaceship collides with the ground. But, of course, that is not what we want. So, I'd like the density to start at 0 and gradually increase. We can accomplish this by animating the density property. When the spaceship comes to a halt, we must do the opposite, gradually decreasing the density. Before we proceed, we must consider an important question. When we change a parameter and test the simulation behavior, we must also consider the actual resolution. That is, the behavior of a simulation is also affected by its resolution. The voxel size influences not only the final resolution, fine details, but also how the fluid moves and interacts with other objects or forces. Indeed, the voxel size is also the smallest size at which Blender can compute the simulation. As a result, changing the resolution may cause the fluid to behave differently. This is why, at some point, we must raise the resolution to check the final result. Let's look at the simulation. And this is the result with the density animation. We also have the surface and volume emission properties. The term surface emission refers to the distance from the emitter's surface where smoke is produced. The volume emission specifies the additional volume required to generate the smoke. In our case, however, we can leave these properties at their default settings. In this case, we really need the initial velocity. It represents the added velocity to the smoke. Let's see how the smoke is coming out now. It is currently created in the position of the emitter. However, once created, it does not move and remains at its original location. So, let's take a look at the initial velocity property. The source velocity adds a speed to the smoke in the same direction as the emitter. We can also add other velocity directions based on the normal or world axis. In our case, I'm interested in the source velocity. Here, we can see the smoke moving forward and colliding with the domain boundary. We don't have a tail behind the smoke. This property can also be animated. Finally, I'd like to expand the domain along the x-axis, so that smoke can flow in that direction. And here is the end result. The sampling substeps parameter is also useful. It is the number of computations performed for each step. It is mostly used when dealing with fast-moving fluids. Increasing the substeps in these cases allows Blender to better compute the interaction with other objects or forces. But in our case, this is unnecessary. Let's return to the domain. We also have some properties to improve the computation's quality. And they are the CFL number, maximum time steps, and minimum time steps. I won't go into detail about these properties, because that would require a longer explanation. I covered these topics in the smoke, fire, and liquids classes on the platform. Essentially, we define the maximum and minimum number of calculations for each frame, and let Blender decide which exact value to use. However, as we saw with the emitter's sampling substeps, this is useful when dealing with fast-moving fluids, because it improves computation accuracy. The border collisions property has already been mentioned. And we don't want the smoke to collide with the boundaries of the domain. So I'll uncheck these properties. The adaptive domain can be an excellent choice. This automatically scales the domain to make it large enough to accommodate the simulation. For example, at the start of the simulation, we only have a small amount of smoke. Blender automatically shrinks the domain in this case, reducing computation time. And this is what occurs. The domain is scaled based on the simulation's effective size. However, in some cases, we have a problem. It is possible that a portion of the fluid will be abruptly cut off. This is because there is very little smoke density in that area, and Blender treats it as an empty space. If you run into that problem, consider disabling this option. Then there are some other physical properties of smoke to consider. The buoyancy density of smoke defines its tendency to rise upward. The greater this value, the faster the smoke rises. A value of 0 indicates that the fluid has the same density as the surrounding environment, and thus does not move at all. The heat property refers to the temperature of the smoke itself. As a result, higher values result in a fluid that moves faster upwards. The property vorticity adds turbulence to the smoke. Remember to only slightly increase this value, as doing so can result in unexpected results. Basically, I reduced the buoyancy density property so that the smoke rises slowly. In regards to the heat property, the source emitter has a similar attribute called temperature. So, why do we have a property that is similar in both the source and the domain? This is because we may have multiple fluid emitters in the same domain that we want to control separately. As a result, increasing the heat property at the domain level increases the tendency of all fluids within the domain to move upward. On the other hand, we can change the temperature value to fine-tune the individual emitters. Let's now look at the other parameters. We've already discussed the dissolve option. After a while, it allowed the smoke to dissipate. We can see here that the smoke persists for a long time at the end of the simulation. For example, we could animate the density property, as shown at the start of the animation. However, we can do this automatically by activating the dissolve property. The higher the time value, the slower the smoke dissolves. we can see that the smoke is dissipating faster than before. And, at the end of the simulation, it vanishes completely. If it dissolves too quickly, try increasing the time value significantly. Let's disable this option for the moment, and move to the next property, the noise one. It's a useful property, because it adds noise to the smoke while also increasing its resolution. We do, in fact, have the uppers factor value. It's essentially a multiplier of the simulation resolution. This will come in handy when we cache the simulation, as we'll see later. Indeed, we can cache the simulation's individual components separately. For example, we can bake the simulation with a specific domain resolution. The noise is then baked separately. So, if we want to add more resolution, we only need to increase the uppers factor and bake this individual step, rather than the entire simulation. It comes in handy when we have complex simulations that can take hours to compute. The other parameters, on the other hand, are associated with the noise. This essentially changes the shape of the smoke, which is very useful for achieving more natural results. Of course, these values can be increased to simulate extreme physical situations, such as very turbulent smoke. And here's an example of how noise can change the shape of the smoke. The irregular distribution of smoke, in this case, is due in part to the noise factor. Before we get to the cache section, I'd like to discuss the third option when we add a fluid object. We've already seen the domain and flow object. But there is also the effector. It is an object that can interact with a simulation in two ways. By coming into contact with the fluid. Alternatively, by adding velocity to the simulation. If we have a fluid, such as smoke or liquid, in this domain, we may have an object that moves in this direction. And by moving, it adds velocity to the smoke in the same direction. It can be used as a colliding object in our case. We do want smoke to rise, but we don't want it to move inside the spaceship. As a result, the spaceship's body must act as a barrier for the smoke. Simply select the object, apply the fluid effect, and then select Effector. And for effector type, we must select Collision. The other option is Guide, which basically means using the object to add velocity to the simulation, as previously mentioned. Let's start the simulation again. We can't see the smoke colliding with the spaceship, because it completely covers the mesh. However, it will be more visible in the final rendering. Here, we also have the sampling substeps property. This is, as you already know, related to the number of computations. And, as previously stated, it is more useful for fast-moving objects. In this case, more calculations are required for each frame in order for Blender to detect collisions. The surface thickness parameter increases the volume around the mesh for collision detection. And this is useful when we notice that smoke is passing through the surface. This is a simple checkbox that allows us to enable or disable the effector. And this is the option to choose when we have a planar surface. When we choose Guide as the effector type, it does not actually collide with the smoke. It does, however, cause the smoke to move in the same direction as the guide object. To make a guide object work, we must enable the Guides option in the domain. This is because the Guide option enables a more precise algorithm than the standard one. It also takes into account the presence, if any, of the guide objects. We have some parameters here that change how the effector works. For example, increasing the velocity factor multiplies the effector's velocity. As a result, the velocity of the smoke increases. However, since we do not require a guide, we can disable this option. We must now cache the simulation. As previously stated, we can specify the start and end frames. Blender also creates a cache folder in the same directory as the Blender file. The type of cache we want to create is the most important property. We have 3 choices. The default option, Replay, means that the cache is created while the simulation is running. This comes in handy when we need a quick preview of the simulation while we're working on it. It is also best suited for simple simulations. However, keep in mind that this is a temporary cache. The cache is deleted if we close and reopen the Blender file. If we want a permanent cache, we must select Modular or All. Let's go with the All option. We now have a Bake All button. The smoke simulation is saved to disk when you press this button. The label All indicates that we are baking all of the simulation's components, including the fluid, noise, and in the case of fluid simulations, the mesh and particles. The final option is Modular. This means that we can bake each component of the simulation separately. Indeed, there is now a Bake button for each step of the simulation. This is the fluid section, where Blender computes the basic fluid itself. Then there's the noise component, which adds turbulence and extra resolution. This is especially useful for complex simulations. In these cases, we can bake the fluid and then fine-tune the noise component separately, rather than having to recompute the entire simulation every time. The option is resumable is the final good feature. This is very useful because we can pause the simulation and then resume where we left off. For example, we could begin baking, pause it by pressing the escape key, and then view the results for only the first part of the simulation. If everything is fine, we can resume the computation from here. We couldn't resume the computation with this option disabled, so we had to start over. We can also rename the cache folder to maintain a consistent file name structure throughout our project. We can now begin baking the fluid component. Now I can see the initial result by pressing the escape key. I also have the resume button, thanks to the resumable option. We don't see smoke when the computation is finished, because we also have to bake the noise component. Let's get started. And this is the final simulation. If we close and reopen the Blender file, the simulation remains, because it has been baked to disk. We can also see that all of the parameters are grayed out, indicating that we won't be able to change them until we free the data. We could, for example, delete only the noise data. And the fluid component data is still in cache. We can now change the noise parameters and bake only this component again. We can also pause and resume as needed. Here we have the simulation's final settings. I increased the resolution to 512 and then began baking. This explains why it's grayed out. Consider that the cache for this smoke simulation is approximately 70 gigabytes. And, yes, you are correct. 70 gigabytes. It can also take a long time to compute. This, of course, is related to the performance of your computer. However, we have finer details with this resolution. This is also due to the noise, which adds some resolution and finer details to the shape. With so much data to load and manage, the computer can become noticeably sluggish when moving through the timeline. In such cases, hiding the simulation in the viewport can be useful. You can do this by opening the domain settings and disabling the simulation's visibility in the viewport. Well, as previously stated, I did not directly simulate the entire smoke in this scene. This would have taken too long, because it would have required rendering everything else in the scene as well. As a result, I created another scene, using only smoke and then overlaid it in post-production. Let's start with the smoke simulation, which we'll use to add to the previous scene. To achieve a perfect match, it is critical to render this smoke simulation under the same lighting and rendering conditions as the original scene. So, let's look at the lighting in this scene. I used the sky texture that we can find directly in Blender as the main light source. You can configure it in the World tab. This can be a good alternative to the standard HDR image. In fact, we can manage a large number of settings, have good global illumination, and it can simulate a real sky. So I copied the Blender file and deleted everything unnecessary. Specifically, the spaceship, the rocks, and the building. I kept the sky and the planet's surface. This is done to maintain the original smoke simulation's illumination and reflections. However, we only require the planet's surface to preserve the light bounces. It is not required to be rendered. So, now is the time to introduce another concept, this time about how to include or exclude certain elements from rendering. To begin, we must create collections to organize the content of our scene. In this case, I have the smoke simulation collection. And another collection with environmental elements. And these elements must only contribute to the scene for the lighting components. They are not required to be rendered. To do so, we must first set this flag for the collection. It is the only indirect option. This means that the collection's content will not be rendered, but will instead be used to compute light bounces and reflections. If you do not see these icons, you can enable them by clicking the filter button. So, let's give the collection this property. The next step is to create a transparent background, in order to composite the smoke over the previous scene. To do so, open the camera settings, and select the transparent option in the film pane. Now let's consider the global rendering settings, which we'll also use for the other renderings. I chose cycles as the render engine. I kept the max samples very low, to speed up the rendering. Indeed, thanks to the denoise feature, we can achieve a good rendering, even with low total sample values. Also, if you have an NVIDIA graphics card, remember to set the OptX value. So we can finally make the new smoke simulation, which requires the creation of a new emitter and domain. We need the smoke to rise, cover the entire scene, and then fade away. As a first step, I made this mesh to serve as the smoke source. We have various irregular meshes, which help to create more uneven and realistic smoke. I added the displace modifier to these simple meshes. To begin, I added a subdivision modifier to these boxes to increase the resolution. Then I added the displace modifier, which will only work if we have a large number of faces to displace. Finally, I animated the displacement to create an irregular fluid emission. To accomplish this, I animated the modifier's coordinates. Indeed, the displacement is determined by the related texture. We can change the final displacement by animating its coordinates, which is exactly what we want. So, let's choose Object as the coordinates property. Then, add an empty object to the scene and animate its position. It can simply move along a straight line. We change the final shape of our meshes by selecting this empty as the target object for the displace coordinates. Now I've added the fluid domain. Remember that we need the smoke to appear and then disappear gradually. Essentially, we must animate its density. So I animate the emitter's density property. Let's now look at the domain's properties. I also animated the buoyancy density, vorticity, and dissolve properties in this case. Keep in mind that the higher the buoyancy density, the higher the smoke rises. As a result, I animated this property to start with rising smoke. The smoke should eventually stop rising and begin to fall to the ground. In addition, I animated the vorticity. I also animated the dissolve property as a final step. Indeed, I realized that animating the density parameter was insufficient. With a density of 0, I always had some smoke. As a result, I animated the dissolve property, beginning with a large value, in this case 100. Keep in mind that the higher this value, the slower the smoke dissolves. So, in the final frame, I decreased this value to 5, indicating that the smoke would dissolve quickly. And here is the end result. I only resized the domain to include the framing we require, which is basically this. As a final step, we must create the smoke material. Now we have to talk about the material of the smoke. So, open the shading viewport and switch to render mode. The basic smoke material is straightforward. Simply add the principled volume shader and connect it to the material output's volume socket. Of course, we can now adjust the parameters to achieve the desired result. The first change we can make is to the color of the smoke. However, keep in mind that this color is not the same as the one in the smoke source. In the material panel, the color parameter refers to the overall color of the smoke. The color of the smoke object, on the other hand, is an attribute that can be animated over time. It essentially depicts the color of the smoke as it flows from the source. To use it, we must include the color attribute in the principled volume's color parameter. In this way, we are using the color attribute of the smoke source. And, as I said, we can also animate it. The density parameter is simply a multiplier of the smoke density, which is defined in the smoke source settings. It's important to avoid raising this value too much, because doing so might result in some artifacts. The density is determined by the density attribute, which we can see here. This is the attribute where Blender stores the volume's density data. If we remove this attribute, Blender will have no data to refer to, and the volume will be a cube. Well, I also added this volume info node, as you can see. Here is the attribute that we can use. They are as follows: color, density, flame, and temperature. In case of fire, the last two. Let's look at why this is useful. As we've seen, the density attribute is essentially a multiplier of the global density. However, in this case, the multiplier has a fixed value. As a result, we multiply the density of each cell in the volume by a constant factor. This means that we are changing the density distribution of the smoke in the entire volume in a linear fashion. However, by using the density as the multiplier factor, we change the contrast of the density values. Indeed, if the density is equal to 2 at this point, we multiply 2 by 2 to get a local density of 4, thus increasing the density. In another cell, the density could be 0.2, and in this case, the final density would be 0.04, indicating that the density has been reduced. By doing this, we are raising the volume's contrast. We can see this by taking 2 screenshots. We can boost the contrast even more by including a power function. Some rendering considerations. First and foremost, as previously stated, we can reduce the samplings by activating the denoise feature. We can also modify the volume rendering quality by increasing or decreasing the volume light paths. This is the number of times the light can be calculated inside the volume. We also have similar parameters for the other light components, such as diffuse, glossy, and so on. Then there are some attributes that are specifically related to shader properties. The step size property specifies the distance used by Blender to compute the shader. As a result, the lower this value, the greater the resolution. And finally, the step rate value, which is essentially a multiplier of the step size. So, once again, the lower this number, the better the shader computation quality. When we see some artifacts in the material rendering, it can be helpful to change these values.